Thank you for having me here. It's a real pleasure to be here. My name is João Pinheiro. I'm a senior technical team lead at equinor, and I'm going to talk about the strategies for data-driven digital transformation in the plant. Maybe we can start a little bit with the company. We are Equinor. We are a broad energy company with 21,000 colleagues. We are committed to turning the natural resources into energy for people and progress for society in more than 30 countries worldwide. We are dedicated to safety, equality, and sustainability. As the largest operator in Norway, a leading international offshore operator, and a growing force in renewables, we are shaping the future of energy. Equinor's strategy is based on three pillars: always safe, high value, low carbon. To reach our ambition goals, we need to stay in the forefront of digitalization, implementing and creating value from digital tools. So digitalization is here to transform the way we work and enable us and support in our strategy and goals. So we need to use data to improve safety, to reduce our development and operation costs, increase recovery and discovery, and reduce the greenhouse emissions. Our digital roadmap is centered around 6 programs, cutting across the company in 3 key enablers: developing digital capabilities and leadership, utilizing the external ecosystem, and developing our unified data platform. For example, on this third objective, we recently built a cloud-based data platform called Omnia. Here, relevant data is made available, irrespective of its source or its point of creation in the value chain. The idea behind this platform is to move from silos of data and across our value chain to one common platform that orchestrates all our data across the value chain. One of the areas and programs in our digital roadmap is data-driven operations. This is about using data to maximize asset value through production, optimization, and maintenance improvements. So let's start with the first one, data. Data, you simply need data to be available if you aim to run your business based on data. So the challenge in Equinor and many other industrial companies is that data is tightly coupled to the applications, where each application has their own data interface, own data model, own data access regime, etc. If we look at the second one, the context. Data without any context is quite useless. You need context to ensure that humans and machines understand what the data means in order to be able to use it. So when you have data and context, then you have information which can be used for analysis and visualization. So making data or information available to humans and machines for analytics visualization, it's critical, so we should use it. Business decisions. The final step is to make decisions faster and better based on insights derived from contextualized data and or analyzed data. So OPC-UA is a connectivity framework for industrial automation data that is really supporting us and helping us to contextualize data available from our industrial automation and control systems. So here we have a drawing which shows us the heterogeneous versus the information world, so OT and IT. So we can start with the physical equipment on the bottom here. So we have the physical equipment, which has a real-time embedded computer controller, and this is sending out information to a core process control, so SAS, a drilling control system, which has its own HMI. And then this data is tunneled through an OT-IT gateway, which is then sent out to process historians, which are IMSs, and this is then sent out to an historian cloud exporter, goes through a broker, and then it's stored in an Omnia data lake. And then also we have the data available on a time series database. So if we have a data consumer in Equinor that requests to have access to a certain amount of data in Omnia, they send out a ticket to the Omnia team. Omnia team prepares an API, and then it's available through this Omnia API to our suppliers, to our data consumers, or whoever wants to have access to this data. Here we have two examples of two sensors which are sending us data. But this is data without information, without context. So if you look at the two tags, you see that these two tags, these 27TT3011 and 27TT3061, they are giving us a value and the quality is good. Okay, so we have value, quality, and timestamp. However, we don't know exactly what this sensor is measuring. So it's measuring what? Is it the valve? Is it the pump? Is it the motor? Is it the outlet temperature, inlet temperature? Is it upstream, downstream? So in order to answer this, we need to have context on this data. So the most powerful game changer to obtain context is OPC UA. So it has an ability to turn data into information, data in context, with the OPC UA information model framework. Its ability is to standardize on information across vendors and products using OPC UA companion specification. And this results in interoperability. OPC UA is an open, international, industry-independent, and secure connectivity framework is supporting Equinor in making real-time contextualized data, which is information available. So this means that 2 out of the 4 pillars to become data-driven are already established. But to do this in scale and speed, we need interoperability. So it is important that we also have our vendors implementing OPC UA so we can lift out the data from the bottom level until our Omnia in a much easier and much faster way. So our plants, they are heterogeneous, meaning that we have many different vendors delivering software and hardware on the same plant and across plants. If each vendor is delivering the same type of data in different vendor and system-specific interfaces with vendor and system-specific information models and semantics, then humans or our engineers need to spend a lot of time interpreting this and mapping and transforming this. So interoperability means that we have similar information organized and defined in a standard way, regardless of what the vendor and the system we're talking about. So we agree on common and open formats, information models, and connectivity standards, and we need to have well-defined, understood interfaces. So an OPC UA server can look like this. It can look like with a very good structure where you have the equipment, you have the system where it belongs, you have attributes, you have a nice structure. So an address space that gives you data context information powered by an object-oriented types and instances information model. So an address space where you can browse relations, you can find the connections between objects to understand how things are connected. But it also can look like this, which is really good. You have a good structure again from one of our vendors where you have the sensor. You also know that it's an analog value and you know it's actually current for phase 1, phase 2, and phase 3. And it's very easy to transform this into our model, which is basically almost the same. Now, there are also other less good examples. For this one, for instance, when we look at the analog values that this UA server is sending to us, it's very hard to retrieve any kind of context from this analog values. We know it's 1 to 27, but what are they measuring? What is the value that you're getting from this? So we don't want suppliers making their data available like this on their OPC UA servers. We, meaning the entire industry, need to agree on standard information models for given domains and assets. This is another bad example. So for instance, when we browse a server with this kind of information, it's almost impossible to know what they're describing here. So in order to be able to transform this into something readable, we have to go through technical documents and we have to map it to something that is understandable. So we know that these first tags actually represent foam, gas, oil, and sand density levels. So OPC UA has been implemented and proven in use at scale on Johan Sverdrup. So this project started production in 2019. This field alone is massive. It produced 30% of Norway's total production. And OPC UA has been a central part of the digitalization strategy since 2015. So we have in total 19 OPC UA servers on the plant floor, aggregated into a single OTIT gateway using OPC UA aggregation architecture. So let's take a look at the architecture. So if we start with the top right corner here, this corner here, we have the OPC UA library. This OPC UA library contains the template of all the objects and types and classes that are defined for all the different equipment that we have in our system. And in here, we have the engineering database. And the engineering database means that it contains all the equipment tag names from on our database. So when we merge our library, which is a template, can be used in any project, with this database, we get a plant-specific mapper, meaning that we have, on this case, Johan Sverdrup, we have combined all the types and all the objects with the library, and then we get automatically assigned types for all these equipments. So meaning that, for example, this well, this equipment, they automatically get assigned a type. So we don't need to do any manual intervention here. It's an automatic process. So all we have to do then is assign the class, which gives out the attributes, which we then show on the upper level. So if you go down here to the infrastructure, we have an aggregated server. So we have down here all the sensors that are sending us OPC UA data. All these sensors are then aggregated, sending out to these servers, these DIG or IX gateway servers. The data is now available here and then is replicated to an OTIT gateway. Then when we combine the data available down here with the plant-specific structure that we get all the types and classes here, then what we get is an information model like this. And then what we do is we send out that information model to a collector. That collector stores in a data archive, and then it makes it available all the way down here for anyone with a tablet or phone or computer. They can access to this data. So they have a visualization tool which they can access to all this data. So you see, with just this 3-step here, this one, and this one, we get all this highlighted area pre-built. That's a lot of work already done here. And then this area here is just built on this server here by assigning classes to the right equipment. Just some fun facts. Our OPC UA library, so the template, consists of 50 objects, 90 classes, and 920 attributes. So it's the same library being used in multiple assets. It's already been used in renewables as well, so it's not strictly connected to oil and gas. Our visualization consists of more than 745 pictures that are connected to this data that we have available. And our tag server has in total more than 190,000 tags, which we will upgrade soon to reach about 1 million. So there's a lot of information, a lot of models already being available on this structure. Our UA asset structure has more than 31,000 equipments. So these are the equipments that are automatically assigned the type when we do the connection between our library and the database. And they have more than 1 million items and references. So we utilize and we benefit from this community. And by open sourcing these information models, we also contribute back to the community. So you can go to this link here and you will find our library, the template library that I was showing you before. You can find it there and you can use it for your own purpose. So we believe that being open is the key to achieve adoption, and we believe in openness is the spirit of OPC UA. There are many end user benefits, but let's just highlight some. So it reduces the total cost of ownership. There's an efficient exchange of data without needing human translators in the middle. There's an increased flexibility in the overall architecture. Easy to replace, it's plug and produce components since the interface and information models are the same across vendors. OPC UA is designed for and used across industries. A supplier can use the same interface and the same information model across customers, across industries. Innovation, opportunities, data-driven operations. By utilizing the intention behind OPC UA, we get easier and cheaper access to higher quality contextualized data from our plant operations, industrial automation, and control systems. So, more access to innovation due to broader communities, ecosystems, and international competence, and more competition. So, companies now need to compete on business value and not making it vendor locked in. Also, the ongoing and future areas that we need to focus on now. We need to scale up the standardization of OPC-UA information models. So there's a huge potential, but we need more and more vendors to start using this so we can scale up much faster and much cheaper way. Closer integration between the plant floor and applications and the service in the cloud. This means that we need to make not only the data, but also the context available from the OPC UA servers. So at this point, our information model is kind of hidden on this silo within the OTIT gateway, but we need to expose it also to Omnia. Usage of automation ML and OPC UA together. So we need to close the loop between the engineering and operations. Alignment towards international initiatives like Namur Open Architecture, Namur Model Type Package, Open Process Automation, Industry 5.0, all of them point as OPC UA as one of the several key building blocks. And end users to have one voice towards the suppliers when it comes to OPC UA. Yes, and that ends my presentation. I hope you enjoyed it, and thank you again for this invitation, and I hope to see you soon. Bye-bye.